So as people are finishing getting their lunch, we should start. My name's Jaz Seacon. I'm a professor of political science and statistics. And welcome to the inaugural DSI seminar, Data, Society, and Inference. The co-organizers are Lee Fleming, who is the head of the Fung Institute. Lee might want to wave. Well, he's going to speak. And then at the Stanford end is Hito Imbens, who just joined Stanford GSV from Harvard. So the idea of this seminar is to bring together people from statistics, computer science, and the social sciences to engage in questions that come up from like big data, inference problems with big data, the computational issues involved, and also just the identification issues, how you make causal inferences or even uncertainty inferences with such data. It's, the field itself is becoming quite interdisciplinary in that a lot of the same problems that economists are worried about for many years now computer scientists are worrying about, and vice versa as our data set sizes grow large. And the data is on a lot of social science applications now. The seminar is going to more or less alternate between Cal and Stanford. So next week, Philip Stark from the statistics department is going to give a talk at Stanford, and we're going to stream the talks at the location it's not at. So next week, this will be streamed at the Fung Institute, which is in the old, it's in the old Naval Archive building. And there'll be food, and it starts at 1 next week. And our third speaker will be Don Rubin, who will be speaking at Stanford, like October 16th, I think. Anyways, Lee Fleming will introduce her speaker.
Thanks very much for coming, and we're thrilled to have her here for the inaugural session, inaugural seminar. Oh, good idea. Stanford, can you hear me now? Oh, calling the farm. Are you there? Oh, Paul? Okay, so they're not going to respond. Good. They're not going to respond. So welcome to the inaugural seminar. We're thrilled to kick off this series. I'd like to thank the Garitas Foundation for sponsoring this. And we're terribly thrilled to have Susan Athey as our first speaker. Susan did her undergraduate degree at Duke University in math, econ, and computer science. It was Stanford Econ for your PhD. By the age of 24, she's a Bates-Clark Medal winner. She's been a professor at MIT, Harvard, and Stanford, and her and Hito just moved back to Stanford, so yay for California. Without further ado, Susan Athey.
Great. So thank you so much for having me here. It's a great honor to help kick off this series. And this is a series that I'm really excited about personally because I've been realizing through my research and also my applied work in internet search how much I need to learn, as well as how much research there is to do in the broad areas that were just outlined. So I've been giving a lot of interdisciplinary talks over the last couple of years. One thing I've noticed is that when I go to computer science venues, they get very offended when I have lots of equations because I haven't put enough time into my animations and my beautiful slides. And then when the computer scientists come to economics, the economists get very offended because they're putting all these animations and beautiful slides and they haven't shown them enough of the technical aspect. And I'm not exactly sure where stats seminars fit in the middle. So today I'm going to keep my talk fairly high level. I'm not going to do a lot of equations, but I'm good. Hopefully I will be precise enough that you will be able to follow the put behind it all of the technical details which can be found in my papers. So I'm going to base my talk sort of broadly on some work I've been doing with Dennis Nekapolov, who's in the economics department here at Berkeley. Unfortunately, he couldn't be here today. Should have checked his schedule before I booked the date. I also am going to draw a little bit on a Fisher-Schultz lecture I gave for the Econometric Society, which eventually will come out in Econometrica, and a paper I wrote with Glenn Ellison in the QJE. I'm going to organize my talk. In the first part of the talk, I'm actually going to talk a little bit about some thoughts I have on the intersection of machine learning and econometrics, and sort of pose some sort of open questions and try to connect a little bit, why are economists doing what they are doing, and what can we learn from machine learning? And then I'll kind of switch modes into a specific paper of mine where hopefully those of you from other disciplines will then be able to put a little more in context of what I'm doing and why. So just to sort of start out again, I want to talk about where what machine learning and econometrics do together. And I want to talk about this application to online ads. And even within that, I'll mention that I'm going to base partly on work in progress and partly on an existing working paper. So just as a sort of structural economic modeling, versus sort of classic machine learning. And I'm going to make a whole bunch of generalizations here, which will probably offend a whole bunch of people. So just keep in mind that I'm sort of oversimplifying all of this. Although if I do anything too violent, please object, and we can start a conversation. By the way, I'll take questions throughout. So anytime, please stop me. So an economist generally focuses on wanting to make counterfactual predictions, and that's really the driving motivation behind all of our modeling choices. So I want to recover sort of the primitive preferences of the agents that I'm modeling, so I can say, what's going to happen if I change the environment. So, when I talk to sort of, classic predictive machine learning types, the way I might explain this is that, well, the joint distribution of the features of your model and the outcomes is going to change when I change the policy. So just understanding and modeling well their joint distribution in the current regime isn't enough. So this is going to put a big emphasis on causality. We might have two models that are equally good in the current environment. But a structural model where the estimates have a causal interpretation is going to do better in very different environments. And so economists have focused a lot on finding ways to use only the good variation in the input features and ignore the bad variation, where good might be experimental or quasi-experimental. So, economists you can think about the approaches we take can be roughly put into a couple of different buckets. We have methods based on observational data, like instrumental variables, which are designed to try to pull out of the data what we can learn using only sort of the good exogenous variation. And then you can estimate the effect of a policy occurred. You might have only limited ability to do counterfactuals because you might get sort of only say a treatment effect on the set of people who were influenced by the treatment in that particular setting. But we believe that we'll have causal estimates that could predict something about what this group of people would do in a different setting. Field experiments are also growing in popularity in economics. So field experiments, and I should say, by the way, that in all my referencing and examples today, I'm going to focus on market design. So I don't have any cites to labor, public finance, political science, or any other literatures. So don't be offended. And I'm really not going to do much of a literature review at all. But field experiments in the field of market design, we would be comparing design alternatives. We might estimate models using field experiments as well. And this has been done less, but there's a few examples, and I've done this in some of my work. So we can think about field experiments are going to create variation in the data or generate data from alternative or new designs, which allow us to then do a better job estimating the model. Field experiments can also be used for model validation. And of course, this is something that is the main focus of a lot of machine learning, sort of cross-validation, training and testing. This is like what you do. And so I often find that machine learning people come to economics like, what? You're estimating a model? Where's your test set? You trained your model. I see that. But how did you validate it? And we say, well, we believe the assumptions. And the way an economist validates their model is I sit in a seminar like this and I tell you my assumptions, and then we argue about whether they're right. And then, if I've got a really good paper, I'm going to show you some statistics that validate the model, or maybe I'll have some over-identification, some test, and that's like for the A+, the extra bonus credit. But it's not a requirement. Okay, it's not a requirement for publishing a top economic structural model to have really validated your model in any kind of serious way. Okay, so one of the things that I've done in some of my work with timber is I've used some naturally curling field experiments to validate my models. And in the area I'm working on a lot now, in online advertising, this is a direction that I'm going because we have a lot of changes in the data that are induced experimentally that can be used to test your model. So structural models, they basically make behavioral assumptions like profit maximization or rational decision making. We use observational or occasionally quasi-experimental data to estimate economic primitives, and then we use these to evaluate market design and algorithms. So we might ask, what's the impact of a policy on welfare or profit? We might evaluate efficiency versus revenue trade-offs, or consider market designs not currently in use. Okay? So these are kind of the rough toolkit. And so one of the things, like the sociology of economics, is that these three buckets are almost always completely distinct. There are different sets of people working with each toolkit. They often don't even like each other, let alone sort of, build on each other's work. And so one of the things that I have learned in my experience in industry, and I should say that for those of you who don't know, I've been consulting for Microsoft Search Engine for the last 5 years, and so a lot of my data today, as well as my kind of opinions and thoughts, have been formed from the interdisciplinary work that I've been doing inside Microsoft Search Engine. So one of the things I learned about the new sort of online data world is that the field experiments and the structural models are integrally linked. They're both crucial. Google would shut down without both of them. Okay? So, and they feed off each other in really interesting ways. And so in some sense, it's now for the academic economists to sort of catch up with that and, for our research to really reflect this sort of modern reality. So I'll give you a little bit of color on that. Just to kind of talk a little bit about examples of how these have been done sort of in the past and in the online world. So, in the old offline world, if you like, we had structural models used in research and very occasionally for real policy things. So I've done some optimal reserve price modeling that was used by British Columbia. Some of the structural models have been used and at least influenced practitioners in the design of treasury bill auctions. The structural models are used a lot in antitrust, so evaluating detection of collusion damages in collusion or merger analysis. And so, again, in antitrust, you've really got to have a model to do the counterfactual because you're saying, should these firms merge, you need to have a prediction of what would happen in the counterfactual world where they did merge. Okay. The field experiments in market design are expensive, slow, relatively rare, but when they are done, they can be influential. So there were field experiments in auction design for treasury bills. There have been field experiments in timber, and so on. Online, and this is what I'll flesh out over the course of a couple of slides, algorithms used actually for search engines, for displaying a page in Amazon, for ranking results in eBay, those algorithms actually are structural models. And I'll say in a minute why I mean that. They're sort of the simplest kind of structural model an economist would think about, but they are structural models in the sense that they are used to create counterfactuals. If Amazon wants to choose what their screen should be like, they need to know what would happen if they put the offers in a different order, if they showed you different offers, if they ranked the books in different orders, and so on. And they can't possibly have tried all the alternatives. So they really need a model which is going to understand some primitive relationship between the things that you see on the screen and what people click on and what they do. And it needs to have a causal interpretation. I need to know that, if I move this book up 3 ranks, that will cause more people to buy that book, as opposed to just... Oh, I got a technical... Okay. All right. So presumably somebody will figure out if Stanford's still watching. Okay, very good. So you have to have you want to have a causal interpretation. You don't just want to know that things that are in the top position tend to get bought and things that are in the third position don't get bought as often. You want to know what would happen if I re-ranked them. And that's the same for click prediction, for ranking search results, and so on. So we've had some influence of structural models, and I've had some influence on having them done at Microsoft. Halvarian has had his structural models incorporated at Google. But there's some, Michael Ostrovsky and Michael Schwartz used them to help design reserve prices at Yahoo, but it's still sort of relatively limited. The field experiments are also essential and integral to online businesses. So you do experiments in that you do explore, exploit. So you try ranking things in different orders to actually see some observations of things that you might have thought would be less popular put into top positions. For the selection and evaluation of new algorithms, experiments are required. So nothing ships at Google, nothing ships at Microsoft without going through an experimentation process. Every single change is going to go through a controlled, randomized experiment. And in fact, some of the innovations in experimentation have been happening in these firms to figure out how to overlay experiments, how you can run, dozens of experiments at the same time, and figuring out whether they interfere with each other. Experiments are used to tune algorithms. So I have a general algorithm that might estimate clicks, but I want to figure out, how much weight should I put on certain features. Or I might decide I care more about one objective than another objective. And so the algorithms are usually built with dials that can be tuned. So I want to put a little more weight on a relevant signal. Or I want to put a little bit, I might be balancing users and advertisers. And I want to put a little more weight on the users or a little more weight on the advertisers. And so you have these tuning parameters that can be used to shift the algorithms. And then you'll do an experiment, and you will look at the results, look at measures, and decide which setting of the dial you would like. They're also used to validate structural models. Researchers can create this or exploit these experiments. So we've seen a lot of researchers do field experiments on eBay selling things. We see, the internal researchers of the firm trying out different algorithms through these experiments. Liran Einev and John Levin have been exploiting experiments done by sellers on eBay to try to understand the effects of various policies.
A question.
Yep.
Are there algorithms out there to determine whether they can use the ability to customize their page displays?
That's it. So sounds like you're after my own heart. When I first started working with the search engines, I thought, well, I don't understand why I get the same algorithmic result whether I'm shopping or doing something else, and I would really like to tell Google or Bing what I'm doing and get a more customized page. Sort of the trend is actually that instead you're on a mobile phone and you're going to type in 3 letters, and that's all we're going to get. You don't want to go through various menus and pages. So I would like it if they were customizable, but that doesn't seem to be what the users want, in a sense, at least in the mobile environment. Okay. So let me just show you this is a diagram of click prediction. And I'm going to sort of warm up on some of the ideas with click prediction, which is sort of simple, and then I'm going to go into advertiser behavior. So in click prediction, we have algorithms, which from an economist would call sort of a structural model. It's like a demand model, a structural model of demand that says that basically decomposes the probability of click into sort of the features of the quality of the advertisement or the quality of the link and the position effect. And so if you have a model that can decompose the advertising characteristics and the position effects, then you can figure out what would happen if I re-ranked. That model is going to have some assumptions. So it's going to have, if you want it to work, you're going to want to make some assumptions about independence. And so the models that are used in practice have a bunch of assumptions built into them that allow them to make predictions without having too complicated models. Okay? So and then these models, Halvarian once said he's running the world's biggest logit model. So these models have a zillion features, and they're trying to predict clicks for a very complicated space. So you might have you have tens of millions of unique queries coming in every month. You have a whole corpus of tens of millions of advertisements, and they could be ranked in a large number of ways. So it's a very, very rich space that you're doing. And so innovations, like a typical kind of ordinary course of business innovation might be you put more features into your algorithm. So then you might have algorithm A versus algorithm B. They're being compared through maybe an experiment. So we'd have a short-term experiment where maybe for a couple of days, 1% of users sees algorithm A and another set of users sees algorithm B. An algorithm, in terms of experimentation, the algorithm actually might have exploration built into it as well. So there's an experiment within the experiment. My algorithm, inside the algorithm, will generate randomness to see data. So then those scores will come out of these algorithms that will tell us something about the actual character, whether this ad is a clicky ad or not, pulling out the effect. So what's the causal effect of this ad on clicks as opposed to the effect of what position it was shown in. That's good. Then once you get these scores coming out, you're going to run them through an auction, rank the content, and then users will click on them. Okay? So out of that will come some summary statistics. So we'll calculate how many clicks the ad got in each position and broken up a few ways. That's going to feed back, that data will feed back in real time to the algorithm. So the next hour, the next day, the statistics from this day will then be fed in. So the algorithm itself hasn't changed, but the input features to the model will be updated on a continual basis. And then, so then at the end of this short-term experiment, where the algorithm itself was generating data and sort of updating as it went along, we will look at the metrics and say, well, how did this look for advertisers? How did this look for users? How did this look for revenue? And should we roll it out? Now, if it's a click prediction algorithm, though, we have to think about, well, what is this going to do to the advertisers? So when you were doing an experiment on 1% of users, all right, the advertisers didn't notice. Okay, so the advertisers didn't respond. So all the metrics you generate out of this experiment will be metrics about what happens if the advertisers don't change anything. But of course, if you change the way an ad is scored, that's going to change the incentives of the advertiser to bid. And that's going to be the topic of the paper I'm going to go into in greater depth. Okay, so for now, just accept that the advertiser incentives change. So the revenue and the advertiser profit metrics that I get out of this experiment may be completely wrong. They may be backwards from what would actually happen if I roll this algorithm out to the whole system and the advertisers see it and respond. So just to capture that part, the user clicks would then, and the prices will come out, and the advertisers will see those. Okay? If we actually roll out the algorithm to the whole system. Okay? So if we want to understand the long-term advertiser response, we cannot really learn from that from this short-term 1% experiment. Okay, so how are we going to predict what will happen to Google's revenue as a result of this new click prediction model if the normal experimentation process won't do it? So one thing I could do is I could do an advertiser level experiment. So I could say I'm going to take the advertisers in France and I'm going to give them the new algorithm, and the advertisers in Spain will have the old algorithm, and we'll watch them for a while and see how they work. And the problem with that is that many advertisers actually don't change their bids more than once every 2 or 3 months. So it really is a long-term experiment. This could be very bad for the advertisers in France that you're giving the new algorithm to. They could be very upset, if you've done something that hurts them a lot. And so this is, and it's going to take you a long time to learn. Okay? So this kind of advertiser level experimenting is very expensive, much more expensive than letting 1% of users see a different ranking. Okay, where you can learn about that in the course of a couple of days. So the alternative to these very expensive advertiser experiments is to use a structural model, which would then allow us to understand, if I understand the advertiser preferences and I understand how this model affected them, I can use the data from the experiment to predict how the advertisers respond. And how they respond, of course, will then feed back into the rankings. Okay, so this is sort of a overview in a real online services business of the interaction between the experiments and the structural model. Yes, you could use experiments for everything, but it's not practical. But even for using a structural model, the experiment is going to generate the data that you would use to feed into the structural model to predict advertiser responses. Okay? So any questions on that overview? Okay? So it's a complicated world. And lots of room in each of these kind of pieces for interesting research and innovation. Okay?
So, you just go back to this,
Yep.
Then, you have various versions of this, right? The prediction of clicks could be recommenders. Are you saying there exist systems which actually take user feedback and adapt right now in for example, Microsoft?
Sure. Yeah, yes.
Beyond relevance feedback.
Sorry?
Beyond relevance feedback.
No, absolutely. I mean, the whole point of the whole way that the ad auction works is that the biggest input, the bids are the input, and of equal importance is the probability of click. And you want that probability of click to reflect the popularity of this ad recently. You don't want to use 3-month-old data. I mean, you've got new advertisers that came in the system yesterday. So absolutely, they have to be updated all the time. That's why, some search engines are like this, the ultimate self-improving product. Every time you do a search, you are generating the data that makes the next search better. And
Proprietary. So are they really using reinforcement learning type models? Or, I mean, the question is you can do something myopic, but the question how do you do it in a long-term basis is a tricky issue, right?
yeah, so I mean, I don't think you can think of this as being myopic. But you know, there are dozens and hundreds of algorithms at all of these different firms, so it's hard to completely generalize. Let's say, I mean, just in terms of also thinking about the real-time nature, like if you start typing in, if you type in M-I-C-H, okay? You know, normally that might be Michael Jackson. First of all, you would figure that out from just, you know, people doing searches, that often leads to Michael Jackson. On the day Michael Jackson died, you want to figure out not to take people to, you know, recordings of Michael Jackson, but actually to news about him dying. So those algorithms, the ones that do the completion or that show news, those are updated super fast, so that, you know, within 5 minutes you figure out that Michael Jackson died and you got to take people somewhere else. Okay, so that's what data is just hugely important for that. Okay, so let me now, I'm going to sort of talk a little bit about these machine learning econometrics issues in the context of click prediction, which again is, I think, it's sort of like the most basic algorithm, but I think it's really concrete and easy to understand. It's not so interesting economically, but and then I'll dive into the more complicated problem of advertiser behavior. So the problem with observational data in click prediction models is that more clickable ads tend to be in high positions. Okay, so if I just tried to estimate, you know, how clickable is this ad based on the observational data, I'm going to tend to see things in top positions as being better, even if I sort of control for the position. Another problem is that the ad rankings and the screen layout respond to the characteristics of the individual users. So if you're someone who doesn't click on ads very much, I might not show you as many ads, but if you click on ads more often, I might show you more ads. And these algorithms are getting more and more sort of user specific. As well, you know, I'm going to look at your location, and so I'm going to show ads that are targeted to your location or tend to be clicked on by people in your location higher if you're from that location. Okay, so it's a very rich space of features that go into what's shown. So if we just use observational data, we could get biases. If we only use an experiment, it's too expensive and it's also not sufficient. I just told you the space of permutations is just, you know, more zeros than we can write down. So, you know, something that can be done is to have a dedicated experiment plus a model. And when you have a new, very different algorithm, there's sometimes, you know, a big investment in generating experimental data to kind of to initialize the model. But generally, the practice, again, this is sort of industry lore generalization from talking to people at conferences at all the major online services companies, is that every major online service company that has a screen is going to be doing some form of click prediction. You know, there's some exploration and there's some experimental data generated, but it's generally the case that all that data in the end gets pooled into one big pile of data, which is then used to estimate the models. And there's no notion of instrumental variables or, you know, real way to operationalize the notion of causality into these models. And, you know, conceptually it's not so hard, but, you know, if you're running the world's biggest logit model, like if you add a computational complexity to that, it's going to, you know, it's going to create headaches for you. So, you know, one proposal that I have, at least for historical analysis, is that you can reuse existing experiments and combine that with a model. So rather than just using like here's, you know, a dedicated experiment to generate data, we can bring in the idea of just which experiment occurred in the past as an instrumental variable. And so the idea is that we're running, you know, dozens of experiments all the time. They weren't designed for the click prediction model. They were designed for other things. But most of these experiments generate some variation in the ranking. So that, if we build on that, we have a much bigger data set we can use for estimation, and we might have enough instruments to get identification. So we can think of like a basic structural model that the being clicked depends on a position effect and an advertiser effect. Okay? And so these usual level experiments can be instruments for the position. And so the approach that I did an example of this in my Fisher-Schultz lecture. Basically, first I estimated the click-through rates for each ad, and I separated it into sort of an ad effect and a position effect. And then I'm sorry. First, I used the instruments to estimate the add position variable using the past user level experiments cross adds as instruments. And then I decomposed, just using a regression, this combination into the position effect and the add effect. So I'll just show you for two search phrases kind of what the results look like. And what I've called OLS is actually like what most people would think of as being a well-identified model, because I'm going to have fixed effects for the add and I'm going to have fixed effects for the position. So you would think that I've already soaked up like the main unobserved heterogeneity, and under some models that should be enough. But then I re-estimated using the past experiments as instruments, and what I found was that the IV estimates for position effects looked quite different from the OLS. So the interpretation of these coefficients is that's the fraction of clicks you get in that position relative to being in the very top position. So the OLS says that, if you're in the side position 1, you get 4% of the clicks you would get if you were in the very top position on these queries. But the IV says, no, it's not nearly so bad, that if you take the guy in the top position for iPhone and you move him to the side position, he would get 40% of the clicks he would get in the top position. Okay? And so that's basically saying that even with the add effects and the position effects, that we've still got an endogeneity problem. Okay? So this is completely non-representative, by the way, because iPhone and Viagra are sort of, well, especially iPhone is more of a branded term. So the thing in the top position, if you move it down to the sidebar 1, it's still, it might be that users really want to find that thing, and so they'll search down the page. So the position effects depend a lot on what kind of query it is, whether it's branded or not, and the distribution of advertisers. Okay? All right, so this is just sort of a suggestive idea about how you could think about bringing IV into machine learning. In the real world application in a production system, you would probably not be fully identified with the IV. And so I would say an open question is sort of, how can I leave my production systems, let them use all the data, but have a better identified model? That's that would sort of that would be a topic that I think would bring together econometrics and machine learning in sort of an interesting way, and the computational issues. So I want it to run on 6 billion queries a month. Okay. All right. So just again to open topics, Hal Varian, hopefully we'll have him come into this seminar in the spring, and he's been thinking a lot about the intersection of econometrics and machine learning for time series and prediction issues. So I'm not going to say anything about that. I'll let him advertise it when he comes. But for me, in my empirical micro questions, machine learning helps me. I want to figure out how I can make the best use of observational data to get causal estimates. And how can I incorporate some notion of instrumental variables into these big, complicated models? From the econometrics side, I think that what I've taken from machine learning so far, I've taken a bunch of things, but some of the highlights would be more of an emphasis on testing and validating structural models using experiments or multiple regime changes. So the multiple regime changes is something Dennis and I are exploiting in our current work. Algorithms change. I know when the algorithms change, and I want to see how the advertisers respond to that. More emphasis on learning objectives rather than assuming behavior. So in an economics audience, I can assume profit maximization and nobody's going to fight with me. But if you go out into an interdisciplinary world, you've got to justify your objectives. And so I want to estimate the objectives rather than assume them. And I'll tell you a little bit about that at the end of the talk today. Data-driven model selection and segmentation within economic frameworks. So if I have, if I'm doing a model with tens of millions of bids, tens of millions of orders, I want to let the data choose my model for me. And how can I do that? Econometrics isn't great on this topic. Machine learning on this topic doesn't have as much of a notion of causality and validating structural models. So that's another thing. How do I deal with large numbers of features, and maybe establishing some formal properties of the machine learning methods if I use them? Okay, so that's my big philosophical introduction. Now let me jump into the search advertising. Yep.
When you think of new environments, are you actually trying to use the data for these experiments on one product to predict what would happen if you had a particular auction go for a completely new product?
I'm thinking, well, so in the online advertising, my thing, it might be that I want to change my reserve prices by a lot. I want to have a completely different reserve pricing algorithm. Or I'm,
The same product.
for the same product, say different prices, or a different click prediction model. But I might also, I might think about what if I wanted to, we're always talking about, isn't it sad that we don't have Victory auctions, that we're using this crazy generalized second price auction I'll tell you about in a minute. What would happen if I made that switch? Those are the kinds of things. And that would be very hard to experiment on because you wouldn't be able to educate the advertisers about the new game. Okay. So platform markets, market design matters, and participation is crucial. So here's some search ads. You've all seen those before. We want to think about managing this marketplace. So, the task that an economist would have in thinking about, say, the search advertising marketplace or the eBay buyer-seller marketplace or the Amazon seller marketplace, any of these things, we want to think about being able to understand what is important for managing the market, how do I measure it, and how do I predict it. So some of the insights out of the previous market design literature, we want to sort of conceptualize the size of the pie versus the distribution of rents. So the short-run distribution of the rents affects the long-run size of the pie. So there's a direct thing for the platform, like how much revenue do I make today? But I also care indirectly about the user welfare and the advertiser welfare, because if they go away, I have no market, right? So, and especially in these markets with lots of economies of scale, that's incredibly important. And so one of the things that's true is the indirect channel often dominates. So designing markets for participation can be very important. So some of the things I want to highlight in internet search advertising is that there can be substantial trade-offs between efficiency and short-run revenue. There can be big incentives to price discriminate or to favor market thickness over efficiency. And there can be also things like incentives to show too many irrelevant ads in the short run that are bad in the long run. So incorporating the long-run bidder and user responses leads to radically different design choices. Okay? So if I want to make money today, I can just fill up the screen with ads. Okay, and they can even be very bad matches for the users, and I get a lot of revenue today, but the advertisers notice that those clicks don't convert very well, they lower their bids, the users notice that they're not finding what they're looking for, and they go to another search engine. Okay, so understanding those long-run responses is very important, but those long-run responses are exactly what you're not getting out of a 1% traffic experiment that lasts for 2 or 3 days, which is like the bread and butter of experimentation in online services. Okay? So let me tell you a little bit now about the generalized second price auction. And I told you I'm not doing a lot of math and a lot of equations, but I need to tell you a few things about this because they're going to be very important for the modeling and the counterfactuals. So if you haven't seen this before, this is a little mini education in how these things work. And even if you have, you may not have focused so much on the scoring, which is often abstracted from in theoretical models. Yep.
The bidders, the advertisers might not notice if you change just 1%. Is there ever enough collaboration where you actually, you track a particular click-through to see what happens on their end so that you actually, even in a 1% experiment, can see how it's affecting them?
So, a search provider, some advertisers enable something called conversion tracking, which sends a signal back to you, the search engine, if they hit a certain point on your web page. And then you also have some degree of visibility into what they do afterwards by, for example, measuring the dwell time, how long people spend on the landing page. So both of those signals can tell us something about how happy the advertiser should be with the clicks they've been getting. But generally, the advertisers themselves wouldn't know which 1%, they can't group the traffic, so they don't know, that this particular 1% came from an experiment. They just see aggregates. So the advertisers really don't know unless you cooperate with them in some way to give them the data. And only a very big advertiser would have enough data to really be able to see something specific in a 1% experiment. Okay, so this generalized second price auction, what they run in search is a click-weighted, generalized second price auction. A bunch of terms there. So let me explain for a little bit about how they got there and then how it works. So in the very beginning, they were selling impressions. So I could just sell, you could pay 10 cents to be displayed in the top position, the second position, or the third position. That can lead to very thin markets. If you imagine that you had 5 advertisers bidding on a page, they could just sort of decide each to bid for one position and not really compete with each other. So the insight very early on was that let's sell clicks instead of impressions, instead of spots on the page, because that's going to, then I can just sell clicks, and you could be in any spot on the page, and the main difference between spots on the page is that you get different amounts of clicks. So I'm going to take 5 heterogeneous objects and make them homogeneous, and therefore get a thicker, more competitive market. That's been termed conflation by Levin and Milgram, and this is an insight that's used in market design in a whole bunch of different markets. Okay, so then, but if I want to sell a spot on the page, the opportunity cost of that space is putting somebody else into that spot. So I still need to think about the revenue I will get from showing someone, not the, as a search engine. Okay, so I have to convert a per-click bid and a per-click payment into a per-position, a per impression, they call it, payment. Okay, so what we're going to do is we're going to multiply the per-click bid by the clickability score to get a per-impression bid. So it's up to the search engine to estimate how clickable is this ad. I multiply the clickability score times the per-click bid, and that's my estimated per-impression bid. Okay? And so, of course, I'm going to be thinking about ranking ads in different positions. So again, the clickability is going to be a counterfactual click-through rate that you would get if the ad was shown in the top position. This ad might never have been shown in the top position, but this wonderful sort of not really causal model I just showed you, structural model, is going to give me a prediction for each ad of what it would be if it was in the top position. Okay? So then and the generalized second price option is that you're going to pay the minimum to maintain the position. So actually, I just had drinks the other night with Hal Varian and Simon Wilkie, and I got more of the inside scoop for how this auction was invented. It appears to have been invented in parallel by Matt Jackson and Simon Wilkie and Hal Varian, no, actually not Hal Varian, by another Google engineer. Hal Varian analyzed it and blessed it, and it was released in around 2002 by both Google and GoTo.com, which became Overture at that time. Okay, so this was a mechanism that was meant to be stable, and it's stable in the sense that the only reason your price is going to change is if you actually change position, and that kept bidders from gaming the system and needing to change their bids all the time. So just here's a little table. So per-click bids, B1, B2, B3, these are 3 different advertisers. Then I use the system-generated scores to calculate rank scores. So the rank score is the estimated revenue bid, the bid per click times the estimated clickability of the ad. What's the minimum bid you could have made to maintain your position? Well, I just have to equate the first bidder's rank score to the second bidder's rank score and solve for the first bidder's bid, which gives you this price per click, B2 times S2 divided by S1. Okay? Now, if I want to say, so this is allowing everybody to be paying the minimum amount that they could have bid to maintain their position. At the bottom, we've got a reserve price, and so the guy at the bottom is going to pay a reserve price divided by his score. Already notice that the prices all depend on these quality scores. These quality scores are set by an algorithm by the search engine, not necessarily revealed to the advertiser. They can also be completely granular. So I can make this at the level of the advertiser cross search query. So Nike has their own quality score on tennis shoes, the query tennis shoes, and so if Nike was in the 3rd position, they would be paying my reserve price, which can also be specific to the query, divided by the quality score, which is Nike's quality score on the query tennis shoes, and that's his price. Okay, so this is very much of a managed market. Even though it's an auction, all the inputs to the auction are set by algorithms which are designed by the search engines. Okay, so you can, in principle, if you thought these bids were static, you could do perfect price discrimination, and every once in a while an engineer wakes up and says, oh, did you notice, they're bidding B, and we're only charging them this, why don't we charge them more? Okay, and as an economist, then you say, well, they might change their bids, and then they say, but these guys don't change their bids very often, are you sure they'll change their bids? And as an economist, then I want to come back and sort of show them all my evidence about how the advertisers respond, which is partly the motivation for some of this research. Okay, so these are the prices. Then if I want to think about how much revenue I'm going to get from each position, all right, I want to multiply the price per click times the probability of click, and that will give me the estimated revenue I would get from this ad being in the 1st position. So the first bidder is actually generating revenue equal to the estimated revenue bid by the second guy, and the second guy is again generating revenue that's determined by the revenue bid by the third guy. So it's really a position auction. It's just that they're bidding and paying in clicks. I've got these alphas over here. This is just to indicate that the second position is going to get less clicks than the first position, and the third position is going to get less clicks from the second position. Okay? So when you think about the search engine's revenue, you can say, well, you know, if I did something to this quality score, you know, to make it bigger, that would generate more revenue from the first position, and whatever it does to, you know, to the rest of the auction doesn't matter as much because the first position is generating the most clicks. So it gives you a lot of incentives for price discrimination. There is no commitment by the search engines that these quality scores are actually clicks, that they're actually probabilities of click, and in fact, they're not. They incorporate other stuff, which could be related to price discrimination, could be related to other notions of efficiency, but it's not just clicks. Okay? All right. So now I want to think about, I'm going to get data about these auctions. I want to estimate advertiser preferences, and I want to do counterfactual analysis about what would happen if I changed the system. And I just talked to you about some of the things that, you know, you could think about if you were a search engine managing this marketplace. Okay, so I talked a lot about the incentives for price discrimination. Actually, if you're trying to compete to get advertisers on board, there can be actually less of a focus on trying to extract revenue from the advertisers and more of a focus on just trying to get volume and profits out to the advertisers so that they will stay with your platform and spend more money on your platform. Okay. So the economists are always interested in the price discrimination, but that's maybe more of your focus if you've got a bunch of locked-in advertisers and less of your focus if you're small and you're trying to get advertisers to be interested in you. Okay? And as I said, it's very difficult to learn about these things from experiments. So what I propose here is a structural model, and so this is a paper with Dennis Nekopolov again here at Berkeley. I'm going to tell you a little bit about our structural model, and then I'll talk to you about what we're doing in current research to extend it. So in our model, we factor in some real-world aspects of this problem. For the advertisers, we factor in the same bid applies to lots of user queries. I model the uncertainty faced by advertisers. We do existence and uniqueness of equilibrium, which I'm not going to show you today at all. We develop a structural model, show identification, the properties of the estimators. What I'm going to focus on today is show you a little bit about the estimation of the values using Microsoft data and the counterfactuals that we do. Okay. So here's just a little bit of a kind of schematic to think about think about this problem now from the advertiser's perspective. So what's going to happen? We're going to have this advertiser order database, and somebody like LendingTree might have multiple ads that they're putting into this system. The user enters a query. The delivery engine queries the database to find the applicable bids. The scoring algorithm produces the scores. The ads are selected, ranked, and scored. The ads are displayed, and the user clicks on the ad. And of course, this is all happening in real time. Okay, so just, you see how fast the page comes up, but all of that happens in the background while you're, between the time you hit enter and the thing comes up. Of course, with Google Instant, even before you hit enter. So some of the things I want to emphasize now, I've talked about the click prediction algorithms. Those algorithms, of course, are not static. So the scores are going to change over time. And so the advertiser is going to understand that their same bid is going to be subject to score variation. As well, the scores might depend on user features. So your score will vary depending on which user, or what the location of the user, the geography, and so on. So there's a lot of uncertainty in this environment. And I emphasize that just because most of you actually may not have seen the prior literature, but the prior literature by Halvarian and Edelman, Ostrowski, Schwartz had focused on sort of the case where there was no uncertainty. And so the uncertainty actually made the modeling a little bit easier as well as more realistic. So from the advertiser's perspective, they have these tools. So this is a screenshot from Yahoo's old interface, which was particularly nice from the perspective of explaining our model, because this is basically what the advertiser sees when they're trying to think about what to bid. And so they actually have this little slider tool that allows the advertiser to think, hypothetically, what if I changed my bid? If I slid this little slider up and down for different bids, how many clicks would I get? And then if you click on another button, you get the same chart for how much does it cost me. Okay? So the advertiser sort of you think about the advertiser faces sort of a supply curve of clicks, and if they bid more, they're going to get more clicks, but they're going to pay more per click. And if they bid less, they'll get less clicks, but they'll pay less per click. Okay? But this is just basically going to be averaged over a whole bunch of auctions like this, where in each auction there might be different competitors and different quality scores. Okay? But for each case, the higher you bid, the higher you are on the page, but also the higher is your price per click. Okay? So we can formulate, so the problem the advertiser's facing kind of literally is to maximize with respect to their per click bid, their value per click times the quantity of clicks minus the total cost, the total expenditure that they have from that bid. Okay? But I can reformulate the problem just to say more directly, to just say, well, they're really buying a quantity of clicks. And the bid is just like a slider tool that chooses different quantities of clicks and different expenditures. So to formalize that, I can just define something like a total cost of clicks, which comes from the objective function here, and say I'm going to maximize with respect to the quantity of clicks I buy, the value times the quantity minus the total cost. From an economist perspective, I can rewrite that as Q times V minus the average cost. And this is really like a monopsony problem with this is a click supply curve. And so the advertiser is going to buy the number of clicks that sets their marginal cost of clicks equal to their value per click. So they're particularly not going to bid up to the place where the value equals the average cost, of the price per click. Instead, they're going to realize that they want to buy less than that so that they can lower the cost they pay for each click. Okay? So now from a econometrician's perspective, if I want this value I don't observe, but I can observe and estimate the marginal cost. And so what I want to do as an econometrician is look out in the data and estimate the marginal cost and then infer what the advertiser's value must have been. Okay? So the way this works is I can take historical auctions and extract a subset. And then I can look at those auctions and simulate what would happen if I changed my bid, increased it a little bit, if each advertiser increased their bid a little bit or decreased their bid a little bit. And I can come up with supply curves of clicks, total expenditure curves for clicks, and then from that I can estimate what the marginal cost of clicks is and estimate the values. Okay? Because I have so much data and I have sort of all the data, I don't really have a lot of estimation problems. I can just do this very non-parametrically. So in my paper with Dennis, we estimate the distributions non-parametrically. We take numerical derivatives. We show that the estimates have desirable properties, asymptotic normality, blah, blah, blah. In our paper that's in progress, we make a more functional form approach. We assume that the shocks to scores, the variation scores, are jointly log normal, conditional on some covariates, which is a good approximation. And there we get better numerical derivatives because we can actually get analytic formulas for the derivative, an analytic formula for the marginal cost of clicks. And then I can use numerical approximations to that analytic formula, which will make sure I'm not like dividing by 0 and things like that. Okay? And both of these methods we've done at small scale in MATLAB, but we've also implemented them at scale on millions of advertiser bids in parallel. So both of these, they're very parallel methods, and part of that is because basically they're just replication and aggregation. I'm estimating, a cost function. I'm estimating a derivative. It's just I've got a formula for that in terms of these random variables, but I'm not having to do like maximum likelihood where I'm optimizing over something. So it's a very parallelizable approach. Okay. So here's an example, and for those of you who aren't economists and aren't used to thinking about marginal and inframarginal effects, I'll just show you quickly how it works in this example. So down here on the x-axis is the expected quantity of clicks you would buy. This blue line is the average cost curve for clicks. So it's showing as you increase the number of clicks you want to buy, how much does the cost per click change? And so if you want to buy a lot of clicks, say being in the top position, and this is expressed as a fraction of being in the very top position. If I want to buy basically almost all the clicks that are available on this query, I need to pay a lot per click. But if I want to buy only half the clicks, I can pay much less per click. So then I can just basically numerically differentiate this average cost curve to come up with a marginal cost curve. That's the red line. Okay? And so if I found a particular bidder who was buying just less than half the clicks, I can say, well, what value per click would be equal to the marginal cost per click evaluated at the quantity of clicks he actually bought? So this guy, he's about in the second position. That's about half the clicks of being in the first position. This teal line is indicating the quality he bought. So the intersection of the quantity that he bought and the red line is my inferred value. So this gold line is the inferred value per click. That's the value he must have had to make this his bid and thus his quantity of clicks optimal. Okay? So the advertiser's profit will be this rectangle from the teal line to the gold line to the purple line. All right? And that's his profit. You can see that if he went all the way out to where his value if his value is still greater than the cost per click, even if he bought all the clicks, his profit would be a skinny rectangle, which is less than the area of the rectangle he gets from buying about half the clicks. This is sort of standard kind of market power effects in economics. Okay? So from this, I infer values. So I can basically calculate these. I don't do the whole global curves and when I do the algorithm at scale. I just look at the quantity of clicks he was buying, what was the derivative of his average cost curve there. I can do that for all the advertisers I see, and for each advertiser come up with a value. Once I know the advertiser's objective and his value, then I can recompute equilibria for any change in the world I want. Now, recomputing equilibria has its own issues. So in our paper, we develop a homotopy method for this. But actually making the equilibrium computation scale up is really an open problem. All the advertisers, like eBay bids on almost everything, and so therefore all the advertisers are in some way related. So solving for an equilibrium in the space of 30 million bids, is a very hard computational problem. So we have some heuristics that help us work, but they're only approximations. So this is, I'd say counterfactual analysis at large scale equilibrium computation is definitely very much of an open area. Okay, so let me now show you some of the counterfactuals that we do. So to start with, this GSP auction, I just told you why advertisers don't bid their values. They actually withhold some demand from the market. They buy less clicks than they might because they are trying to lower the price they pay per click. Something called a Vickrey auction has different pricing rules, and it can make people want to bid their values. Now, the Vickrey auction would actually put me out of business in all of this, because if people bid their values, then I wouldn't have to estimate their values, and I could very easily predict what would happen if I did all sorts of changes. But I would like to be put out of business, because this is a hard business to be in. So if we change to a Vickrey auction, we might wonder what would happen. And it's something that, Facebook switched from GSP to Vickrey and recently, and now they have a much easier to manage system. Microsoft can't really do it because Microsoft has to be compatible with Google. Microsoft is small, Google is big. You want the advertisers to export their campaigns from Google to Microsoft, so we can't change. So I'm waiting for Halvarian to switch to a Vickrey auction. Why does Hal not change to a Vickrey auction? Well, I just told you that you shade your bid. You bid less than your value in a GSP. In a Vickrey auction, you bid your value. So if you change the pricing rule overnight, then people should have been bidding much more, but they're not. So your revenue would fall. It would cost Google probably a couple $2 billion to change. So they probably won't do it. But I can still ask the hypothetical question and think about, what Facebook's change and so on. So Vickrey is always efficient. If you're bidding your value, you get the right allocation query by query. The GSP auction, bidders are not bidding their value, and actually what we show in our paper is that these shading is asymmetric. If the shading is asymmetric, then in some queries, the most efficient guy will not win. So we estimate in our data what is the effect of this inefficiency, and the revenue effects are also very ambiguous. So what we find is that the Vickrey auction is a little bit more efficient, but the welfare effects actually aren't very big. But we find that the revenue effects are quite heterogeneous. So for one search phrase, we found a large decline in revenue from switching to a Vickrey auction, while for another search phrase, we found a slight increase in revenue from the Vickrey auction. And this is assuming everybody optimizes and does equilibrium behavior. So in some sense, the switching to a Vickrey auction could be kind of dangerous. It could, even in equilibrium, once people adjust, could lead to a long-term decline in revenue. Okay? So that's the kind of thing you can do with a structural model that, of course, you couldn't do with just, a general machine learning looking at the joint distribution of bids and covariates and so on. Let me talk about another example, click prediction again. Let's come back to click prediction. So I talked about, how click prediction works. Now let me talk about it from the perspective of price discrimination. So one of the sad facts about the world is that if you make your click predictor more accurate, it can be bad for revenue. Why is that? Okay, suppose there's shoes. I'm selling, the query is shoes. There's men's shoe men's shoe store bidding and selling men's shoes, women's shoe store bidding and selling women's shoes. Say they both get equal profits from that, and there's equal number of men and women searching. Okay? The way this auction works, they suppose their values are about the same, their bids are about the same, their estimated revenue is about the same. The search engine basically extracts all the revenue from the top bidder because it's sort of and you end up getting, you get this revenue right here, the bid times the score. Okay, now let's think about switching to a granular click prediction that identifies user types. So I think you're probably a man and you're probably a woman. Okay, how does the auction change? Well, now there's, if it's a man searching and I give a higher quality score to the men's shoe store and a lower quality score to the women's shoe store. Well, that makes the women's shoe store a less good competitor for the men's shoe store. It thins out the market. In the limit, if the women's shoe store got no clicks, it would be just as if you had no competitor. So you've taken away all the competition in your auction, and you, in this example, reduce the revenue. Okay? So this tells you about this. There's a general trade-off between efficiency and revenue. And it depends on the parameters of the problem, whether it's good or bad for you to make things more accurate. So we did a counterfactual where we basically took, we modeled, well, what would be the impact of putting in a user feature? So we modeled this by representing these click scores as the sum of two components, and then model what's the impact of removing one of the components, which basically adds noise. Okay. So we do these counterfactuals, and we do two steps of the counterfactual. So we're imagining coarsening, making things noisier, starting from an accurate click predictor. So we first look at what happens before the advertisers adjust, and then what happens afterwards. And we do this to kind of emphasize what you would get from a short-term experiment before the advertisers adjust and what you would get in the long term. And so what we find, just focusing on revenue, is that making the click predictor less good decreases revenue when the bids are held fixed. And that's because the inefficiency, getting the wrong guy in the top position, decreases clicks, which decreases the revenue. But in the long run, when the advertisers adjust, it increases revenue. And that's because you've made the market thicker, and so then the bidders shade their bids less, and then you get more revenue. Okay? So there's a crucial role for this modeling. The short and long-run revenue predictions go in the opposite directions, and this is something that can really confound an online services system. The click prediction team comes up with this great thing. They run an experiment. It looks wonderful. They say they're going to get, this, a certain revenue gain, and then it disappears in the long run. Okay? So this is a case where understanding the advertiser behavior is really important. All right.
Susan, what happens if one of the search engines does the coarsening but not the other? Is there an incentive for one of them to?
Yeah, that's a good question. So I think that, generally, I can just speak for what I've seen at Microsoft is that, if you do anything that reduces the clicks to the advertisers, you're very worried about that because you're really worried that the advertisers, you're irrelevant to the advertisers and they're not going to pay attention. So if you're facing competitive pressure, you might be pushed more towards efficiency. But if you're facing less competitive pressure, then you would worry more about the revenue extraction. Okay, and that's a real tension that you see when you're managing a marketplace. Okay, so now let me just say a few more words. I just have a few more minutes. I'm going to summarize the problems with this that I've encountered in terms of both validating my model and putting it into practice, and some of the directions where we're going. So what you'd want to do is test the model. So I come up with my structural model, and all the machine learning people who are kind of the big audience in practice, well, where's your validation? Okay, so I can go out and do validation, and the first problem that you have is this economist assumption of kind of profit maximizing all the time, everywhere, optimizing all the time is not true. So a big chunk of the advertisers just aren't noticing. Their prices changed by 15% and they didn't notice. They didn't change. Okay, so there's a lot of heterogeneity in terms of even when they pay attention. Then there's a lot of heterogeneity of objectives. So some advertisers are trying to be in the top position and so on. So they're not actually, or they're budget constrained. That's a really big deal. Lots and lots of problems with budget constraints. So my model is wrong. Okay? So now what do I do about that? So I could, and there's also, they're all using different agencies and tool providers and so on to implement their objectives. Even if they have the same stated objective, the different tools will implement it differently. So one thing I could do, and I've done a bunch of analysis on this, is I could segment them based on observables. So like the applied econometrics approach would be, okay, I'm going to allow the coefficients of my model to depend on observables, all right? And the problem that I came to here was that I had so many, like my old-fashioned toolkit was inadequate. So I really wanted to use something more like a machine learning approach that's going to use an algorithm to segment the advertisers. And so this is, I think, an interesting area for research, bringing together machine learning and econometrics. So the second approach, and this is what Dennis and I are working on now, is to estimate the heterogeneity of the advertisers at an individual level using a full structural model. Okay? So let me tell you a little bit about how I want to do that. So we're going to specify a set of possible objective types. So the straight profit maximization I showed you before, then the primitive is the V, the value per click. I can have a budget-constrained variant with an unobserved budget. I could have position targeting objectives that have values for impressions in each positions. And some advertisers track clicks while others track conversions, which would lead them to be optimizing, but with a different observed hue. So, and then the model primitives, that would then be for each advertiser, their objective type, the parameters of their objective, as well as a time cost or stochastic process of their attention in order to explain the guys who like only log in once every 4 months. So I'm going to use a Bayesian approach to model this. And for each advertiser, I'm going to come up with a posterior of each of these things. Okay? So how am I going to identify those? Well, I'm going to observe each advertiser over a long time period. And I know, because I help manage Bing, I know exactly when they changed the algorithms. And I know that those algorithm changes occurred, at a particular date that wasn't responding to any particular advertiser's objective. So if I assume that the timing of the system shocks is uncorrelated with any advertiser preference shocks, I can start to identify their objective, because I see an exogenous shock, and then each objective would predict that they change in different ways. So I can identify it. Initially, I think we're working with the preference parameters being constant over time, but in principle, we can allow that to be a stochastic process. The time and attention process, I also see when the advertisers change their bids, and so I can use that to help understand what is their sort of fixed cost of changing bids. And one of the things that's true is that when I see in my data lots of advertisers who are spending a reasonable amount of money and aren't changing their bids in response to fairly big system shocks. So you're going to have fairly high costs to rationalize their behavior, which is something that's kind of interesting. It's confounding. It's actually frustrating if you're trying to run an efficient market and you can't get the damn participants to be efficient. But those time costs are really important. And if you think about from a small advertiser's perspective, they're not getting a lot of, they may be, hundreds or, a few $100s a month of business here, but they're also just trying to manage a business. They're busy. And they just don't have time to be worrying about this all the time. Okay. So we're going to estimate it using Bayesian methods. The output will be posterior distributions over objective types and parameters, and then I'm going to do counterfactual estimates. I have some issues, which I'll just highlight here and leave as open for the future. How do you do equilibrium computation with these heterogeneous objectives? What do you assume that the advertisers know about each other? So our starting assumption will be that the bidders have the same posterior as the econometrician does about the opponent types, but there's a lot of other alternatives, and so on. And then I also have to worry about the computation issue. Okay. So I'm going to use machine learning inputs. Afterwards, once I have all these estimates, what the heck am I going to do with it? I've got millions of posteriors. I've got multi-dimensions for each guy. What am I even going to tell you about it? So I'm thinking about, this is still very much in progress, but using some machine learning techniques to help categorize the bidders and put them into segments that are sort of similar behavioral types. And I also really want to take seriously the training and testing, and I can do this because I have lots of system changes. So I'm going to train over 6 months and then see how I do out of sample with different kinds of tests, and I want to think about how to evaluate my results. Okay, so conclusions, econometric methods have a lot to add to market design and marketplace management. Field experiments and structural models combine very deeply, both in terms of generating the data as well as in validating. And putting together Bayesian and machine learning methods rather than just traditional classical econometrics can potentially allow us to make a lot more progress. So. So for the Stanford people, I think what we decided to do, oh, sorry.
So they'll call in, so we'll take questions.
Yeah, we're going to take a question from here, then we'll take a question from Stanford. So, Rich.
Susan, what can your analysis be informed? How can it be informed by revenue equivalents for options? And how does it, the other side of how does it inform the accuracy of revenue equivalents?
Sure. So Rich was asking about the role of revenue equivalence in these auctions. So there's since it's sort of an interdisciplinary audience, I didn't go too far down that road, but just for those of you outside of economics, there's this beautiful revenue equivalence theorem that says in sort of a static one-shot auction for a single unit, there's revenue equivalence between first and second price auctions. When you go to a multi-unit environment, revenue equivalence doesn't hold. And so there can be then a pay-your-bid auction, a second price auction, and a Vickrey auction, and the Vickrey auction makes use of all the lower bids, not just the one right below you. So that is the same kind of dichotomy we have here. So there's a nice result by both Varian and Edelman, Ostrovsky, Schwartz that says, despite the fact that revenue equivalence kind of generally doesn't hold in these multi-unit environments, that the Vickrey auction and the generalized second price auction are revenue equivalent here. That result hinges on there being just sort of a single incarnation of the auction with a single set of scores. And so what the paper with Dennis shows is that revenue equivalence actually breaks down in an uncertain environment. And the reason it breaks down is because bidders have asymmetric markups. And so if you're say bidding just a little bit less than your value and I'm bidding a lot less than my value, then some scores might arise so that we get re-ranked. And so the revenue equivalence breaks down. But what was kind of interesting was that at least my estimates suggested that from a welfare perspective, the GSP doesn't seem to be doing very badly, at least in the keywords that we studied here. But they could have quite different revenue consequences. So that gets back, I think, to the sort of issues of efficiency and revenue, that the efficiency and revenue aren't always lined up perfectly. So can we hear, so let's test out Stanford. Can we hear Stanford? Can somebody say hello?
I think there's like a delay, so it's going to take.
Okay. So
We'll start with the questions on this side.
Okay. Other questions here?
So it seemed like the effect that you were highlighting when you coarsen, the problem is that these markets get thin.
Yeah.
Right? Can you solve that by using a reserve price?
Yes, that's an excellent point. So, going back to this screen, I could do it. I could basically get back to if I thought I understood everything about the environment. Then when my new algorithm comes in, if I knew they were willing to charge the old prices, I could set customized quality scores and customized reserve prices. I can charge whatever the heck I want in this auction. The auction itself puts no restriction on the prices I charge. So I could, in principle, try to keep prices constant. And then rather than reject and not ship the great new click prediction algorithm, I could, because the managers say it's not raising enough revenue, I could, do both. But I think there is, despite the fact that you can do anything you want with these customized prices, there's a lot of ways you can screw up if you start, using monkeying around with the reserve prices and the quality scores just to squeeze as much revenue out as you can. So in practice, you don't do that perfectly, and the world is changing too fast to completely do that. So you still get the trade-off. But that is in some sense if you want to think of it as sort of a positive from the advertiser perspective, element of reserve prices is that you could, in some sense, some advertisers could be better off if you kept the prices constant but increased the volume of clicks.
Stanford, are you guys online?
Do we even know if anybody's there? We might be talking to an empty room.
Taking as evidence the clarity you're talking.
So nobody wants to scream at me for my mischaracterizations of machine learning? You can do that afterwards.
Thanks so much.